will be Jamie Jennings from North Carolina State University, and who will talk to us about how to go beyond our beloved regular expressions.
Question of the day, will the projector work? Let's try another port. Very good. Okay, thank you. I'm going to see if I can carry this around. Okay, my name is Jamie Jennings. I'm at North Carolina State University, and I recently returned to academia after a 20-year sabbatical in industry, which was a lot of fun. I spent 20 years at IBM in research and then in software development. I might still be there today, but I got time off for good behavior. So I'm going to tell you about a project that I started working on while at IBM, and it really is an engineering project. It's open source. We're building a community of users around Rosie pattern language. If you can read that, I'm not sure. All these slides are at rosielang.org. And if you can't see the screen, definitely look at the slides or you won't get all the jokes. So I started this work at IBM when I was working in a group doing DevOps tooling, and we were mining all of the, what you might call digital exhaust from DevOps tools. So all of the log files and commit messages and issue discussions and issue management, test results, deployment logs, even runtime application logs. We were mining all of that to answer questions about project quality and where you might look for bugs and things like that. That's another story. But in the process of doing this, we had to write lots and lots of regular expressions. And I was part of a team that was producing a prototype. So we had people writing in Scala and Python and Ruby. I think one person wrote in Perl. We don't talk to him anymore. In any case, I'm now at NC State, and the project continues. I am now able to leverage the fact that there's lots of interesting research opportunities here, mostly in applications of PL, not in PL itself. So if you were looking at the agenda for today and wondering, why is this talk on the agenda? That's a valid question. There are no PL results in here. This is an example of PL thinking applied to a practical problem. So you might ask, what's wrong with regular expressions? Other than the syntax and the semantics and the expressive power, nothing. Except for implementation quality, all those security issues. That's a problem. So let's look at a few of the issues with regular expressions. And I could have made an entire talk out of showing you real regular expressions, and each one of them would have been a joke in and of itself. But instead, I'm just going to kind of briefly review the big issues and then show you what we did to fix them. The syntax is very compact, which is really great if you're Ken Thompson and you're writing regular expression, a regular expression engine to use in a line editor in 1968. Syntax is very efficient. One symbol can be used for so many different things, depending on the context. And not just easy to see context, but also positional context. And so I realize that can be confusing for people, but it's a marvel of efficiency. Also, they are write and forget, right? One of the great things about regular expressions is that you can compose one on the command line or stick one into your Python program and never think about it again, right? Until your deployment script fails or your Python regex fails to do input validation and your system gets hacked. Okay. Oh yeah, and the last thing, of course, there's many syntaxes. So if you get used to one, that's great. As soon as you switch to a different language, you're going to have to learn variations on that. Okay, let's look briefly at semantics. You probably have realized that modern regular expressions are not regular expressions, right? And so a bunch of us have been calling them regex to distinguish them from actual regular expressions, as in expressions of regular languages. It used to be that there was only one question about the semantics of a regular expression. You had to know if it was the Perl semantics or the POSIX semantics. Nowadays, there are, well, as of 2017, there are about 25 very popular flavors of regular expressions. And don't worry, they're 90% the same, or 95% the same. They only have small differences in how the same symbols are used. Not a big deal. There's so many variations by implementation that you can't even know what dot matches, right? Does everybody know what dot matches? At least what it's supposed to match? Dot is supposed to match any character, right? It turns out that's not the case. And of course, we could just Google to find that out. And if you Google regular expressions, you'll find plenty of information, 360 million pages, give or take. So I'm sure the information about what dot matches is in there somewhere. In fact, if you look at Python's API, what dot matches depends on flags that are not actually part of the regular expression. And this is true of many regular expression implementations. So re.compile in Python takes a pattern and also flags. The expression's behavior can be modified by specifying a flags value. That's great. How many people compile other programs where they expect the compiler flags to modify that program's output or correctness or behavior? Right? Generally, yes, right. If you work on optimizers, that's certainly something you worry about. But generally, you don't want the semantics to change. And in PCRE, which is supposed to be Perl compatible, that's its name. It isn't really, but it's really close, though, except for those cases, which no one's ever going to run into, right? It takes this much explanation to explain what dot matches depending on the flag values. So this is not a good situation. The last thing that was most important for me when I was thinking about what we could do better than collecting all the regular expressions that my team had written in Ruby and Python and Scala and Perl, we thought about collecting them all, sanitizing them so that they use a common subset of all the features, a consistent subset, and then kind of making a library of these things that we could reuse over and over. One of the things we realized right away is that combining these is fraught. Regular expressions are represented as strings in most languages, so this is not good. They don't combine typically. And when they look like they combine, they work about as well as the gears in this education poster, right? Sometimes they look like they mesh together very well, but then when you go to use them, it somehow gets stuck. Okay, and then finally, as I said, we wrote, each of us, dozens of regular expressions. And so across the team, we probably had 100 because we were each mining different pieces of information out of different data sources. And what we wanted, another thing we wanted, was some persistence standard, some way of not embedding these regular expressions in our program code, but rather packaging them up as here's a bunch of regular expressions that are useful for a particular purpose. Let's package them up, save them in a file, and then we can use them from all our different programs. And you may be thinking, we have this. There is a place on the internet where we deposit regular expressions for later retrieval. It's called Stack Overflow. Stack Overflow lacks some of the rigor of other software version control systems. But it's where practicing engineers go to find regular expressions. So here's one. It's only a few hundred characters long, and it matches email addresses. So just to give you a signal of where we're going with this, in the project that I'm going to tell you about, we decided that there should be packagings and we should have namespaces, and so there's a net namespace and an email pattern. And it's based on the same RFC, and it's a little more readable than that, but you can see that that's where we're going. Okay, I debated whether or not to include this because we're about to waste 10 seconds looking at a video, but here's another example of a regular expression online. There are a lot of comments below this that say, thank you, I really needed this. I needed an expression that matched IPv4 addresses and IPv6 addresses. And I looked at this as I was writing the equivalent ones for RPL, and I thought, this actually doesn't look too bad. I mean, it's a long string of symbols, but it actually looks kind of readable until I started scrolling. It's not so readable now. But people are cutting and pasting this and putting it into their code, right? And mostly people are happy to have this available, except for the person who said, I found a little bug. Now, do you think everyone who cut and pasted this keeps going back to this GitHub page to see if there were any bugs? No. Do you think the original author responded to this bug and fixed it? No. So this is clearly not a good situation. And again, just as a preview, all of these kinds of patterns could be stored in a library with namespaces. They could be things that we could version control and edit, and that's where we're going. Okay. Expressive power. So we talked about how regular expressions are not regular expressions anymore. Regex are not regular expressions. Regular languages are limited in their expressiveness, but there's this great property that you can implement them using a DFA and you're guaranteed a linear time algorithm, which is wonderful. But people don't want the limitation, and they will give up a linear time algorithm in order to get more power. This is a wonderful post. It's the best thing I've ever seen on Stack Overflow. If you have my slides, you can click on this and it will take you there. Every month, somebody posts on Stack Overflow, I'm trying to use regular expressions to parse HTML. HTML is defined recursively, right? So regular expressions are a tough technical fit here. It's not a great fit. And somebody finally got was fed up with this question and said things like, your psyche will wither in the onslaught of horror. Regex-based HTML parsers are the cancer that is killing. Anyway, it degenerates visually and thematically, and it's worth a read. So because people want to do things that you can't do with regular languages, we've had feature creep. In fact, Perl as a language, it looks to me like they started off with regular expressions and they accreted features like barnacles over the course of decades. And so Perl 6 grammars, subroutines, back references, conditionals, even recursion is now part of some regex libraries. All of this is ad hoc, which bothers me. Perhaps it bothers you. Not every audience I talk to is really bothered by that at all. Does it bother anybody in the audience that all this is ad hoc? Okay, you are my people. Okay, so despite the fact that we've accreted all these features, which are power-giving features, right? These enhance the expressive power of regular expressions. Despite all that, we still need static analysis because regex are used everywhere. They're used in lexers. They're used in natural language processors at the bottom of the stack. They're used in input validation, just about every place. And so we have this tension. It's the eternal tension between having lots of features or lots of expressive power, technically, and our ability to prove things, right? Okay, and then just briefly, I want to tell you about some implementation issues. Exponential time algorithms are by far the most common for regex libraries. Intel's Hyperscan Google's RE2 and grep are the only implementations I can think of, and there are 100 others, are the only linear ones I can think of, and there are about 100 that are exponential case worst time. So that is certainly an issue. Most regex are embedded DSLs, so some of the semantics depends on the semantics of the language that they're embedded in, and I'm using embedded DSL as loosely here. If it's a library, then it's not really an embedded DSL, but you're using your string type. You're overloading your string type for regular expressions, and that can cause lots of problems. In addition to the type issues and syntax issues like escaping being related to the language you're embedded in, you also need scaffolding to write and debug your regular expressions. Some work that my colleagues did recently showed that they sampled a lot of large and popular projects on GitHub and found that only 17% of the regular expressions they found were covered by any test case at all. So about a sixth. And of the ones that were covered, 2/3 only had tests for either positive results or negative results, but not both. So these are definitely under-tested. I nominate this to be the mascot of all embedded DSLs. This is a gecko embedded in Amber. There's nothing wrong, by the way, with embedded DSLs, at least not if you're the Amber. The gecko might have a different view. Okay, so why am I working on this? There is lots and lots and lots of data in the world and a lot of incentive, particularly business incentive, to mine it. And the bottom of the software stack for data mining almost always has regular expressions in it. And we found, at least in the project I was working on, that regex use does not scale. If you have a lot of expressions, a lot of people, your project exists for a long period of time, suddenly things like maintainability and testability become much more important than things like compact syntax. Okay, so here's my solution. You don't have to like it. You can invent your own. You are the kind of people who would do that, absolutely, unlike most groups that I talk to. So here's a proof that something can be done, right? It's clearly a difficult task to supplant a technology that has 360 million pages on the internet talking about it, but I'm going to try. Okay, the formal basis, as you might expect, is parsing expression grammars. They're weird in terms of the Chomsky hierarchy, but only because they have a lot more expressive power than regular expressions, but they're formally defined enough that we can prove a lot of things about them, and there are two really good examples of architectures for using them in practice. There's a pack-rat architecture that Brian Ford talked about when he proposed these as a useful thing, and there's a VM-based approach, which is the one that I adapted for this work, which doesn't have the memory consumption of pack-rat parsing, but it can lead to long runtimes for certain pathological situations. However, we can do static analysis to predict some of those in advance. Okay. This is what RPL looks like. When I saw how small this screen was, I added a zoom in, so we're about to zoom in on this for a second. But just so that you get the overall idea, there's comments, modules, identifiers. Literals have to be quoted, just like in a programming language. There's macros, which are not shown, and there's executable unit tests. So if we zoom in on this a little bit, you can see this is an RPL file for parsing JSON. It's really just a few lines because I'm importing word and number definitions from other packages. I define some true, false, and null symbols. And then the grammar for JSON this is transliterated directly from the json.org website, right? Because JSON is just not that complicated. It's ambiguous, but it's not all that complicated. And these tests here, you can test to see that your patterns accept or reject certain strings. And that really helps with documentation. And it serves as a regression test. So if you version control this file, somebody makes a change, they can rerun the unit tests and determine if they introduced any bugs that were already known about before. The idea here is that it reads like code, which means less cognitive load on the developer, less number of rules, fewer rules that you have to memorize, and also it diffs like code. Almost all of our modern software tools are based in some way or other on diff. Okay, in terms of semantics for RPL, so I gave a concrete semantics to pegs, and parsing expression grammars are based on combinators. We all love combinators. Why, you ask? Yes. Why? Symbol crash. Okay. We also like combinators because they let us build things, right? And you don't know in advance what you're going to build, but if your tools are composable, you can build things. RPL has Lisp-like macros in the sense that they operate on abstract syntax trees. They're tree transformations. And the reason we introduced macros at all, partly because they're kind of cool, but partly because we ended up in this situation a lot. In parsing expression grammars, the cleany star is possessive. So if you, by mistake, write something that looks like a regular expression, but you use it in this system, if you write dot star followed by any pattern, and that's just a one-character literal, this will always fail because the dot star is both greedy and possessive. It will consume all of the available input, and then there won't be any input left to match X. So there is an idiom in parsing expression grammars, and this is how it looks in RPL, which says if you're not looking at X, consume a dot, repeat that as many times as you need to, which is only going to end when you either run out of input or when you're positioned to match the pattern X. And because this idiom comes up a lot, I wrote a macro called find. And if you put colon is the function or macro invocation syntax. So if you say find colon X, and X could be any pattern at all, it doesn't have to be a literal, it gets translated internally in a macro expansion phase in a syntactic environment. It does all the nice things. Macros are implemented in Lua for now, which is the extension language for this project. This is a topic of future work, actually. And then finally, the rest of the semantics, we have an import mechanism like Go. We have a prelude like Haskell, which, why doesn't every language have this? I don't understand. It simplifies so many things. Environments are like any Lisp 1, and the binding rules are like Scheme. We have essentially let and letrec. Don't tell anybody. I rename them so that no one would think, oh, this is Lisp. But we all know that combinators are the key, right? The reason that these other things exist in the language are purely because we needed them and I wanted something simple. Okay. Lisp-like macros we'll return to at some point because we need a hygienic macro system. Okay. All of this evolved over many iterations, and at a certain point I thought if this doesn't hang together in an engineering sense, I'm going to have to call this an art project and publish in a completely different set of venues. But it actually worked out just fine. So, in fact, it led to a series of tweets which were really obnoxious. I mean, why pick on grep? Grep is so fast. Grep has had 50 years of hand tuning, right? It's wonderfully compact and elegant. But it's also we've in some ways outlived that flavor of regular expressions, and so why pick on grep? Because it's there, because this is what people use. So I posted a bunch of, can your grep do this? So here we curl Google's homepage, and then we use rosy grep, net.url, and we get out all of the URLs on Google's homepage. So we used our standard library. Here is another example, rosy match. Match is like search, like grep, except it starts at the beginning. It's anchored at the beginning of the line. It's the difference between re.match and re.search if you use Python. Match, here's the pattern. Word.any followed by one or more network, any network pattern. And I'm looking at resolve.conf, which is a network file, and what do you see? You see the output is in color. So internally, we generate parse trees, right? Because Rosie's a parser. But for human consumption, we translate those into colorized output just to make it easy for humans to debug. And you can set the colors to be anything you want. So here's an example where we set net.ipv4 to be bold and blue, but we left the rest alone. Now, in another example of can your grep do this, here's a few lines from my system log file, and here's the same lines fed into Rosie match all.things. So there's a package called all, and there's a pattern in there called things, and things is just a disjunction. Is it a date? Is it a time? Is it a network thing? Is it a word? Is it a path? And since they all come out in different colors, people in the back, if you can just see the colors, that's enough. Since they all come out in different colors, it's easy to see. So as you're working with this stuff as a human, you get things working right, you just change the output flag, and you can get JSON output, which is fully structured like a parse tree. So I asked for denoted hex digits. I get the things that are submatches of that. So I get hex numbers, and I get denoted hex numbers, and then I get the whole scope on the outside. These scopes are exactly derived from the structure of the pattern num.denoted hex. So you can predict this structure exactly using the syntax of the language. This is what data looks like these days. If you work at IBM, you have to include something like this. Okay. Is in here, and it's about 50K, and it'll generate different output formats depending on your switches. Patterns coming in the top. Patterns are all the same. It doesn't matter if they came from the prelude. It doesn't matter if they came from the pattern library that ships with Rosie. It doesn't matter if they came from your patterns or the command line. They all go in and into this engine. The compiler's like 400K. There's a bunch of stuff in there. But anyway, and then the engine runs. So I told my colleagues at IBM that the engine here is only 50K. We can link this in with lots and lots of programs. And they said, 50 meg's really not that small. They said, a JVM is like 50, 60, 70, 80 meg. And I said, no, K. Have you all even remembered? Do you all even remember what K is? Okay. If you look inside the compiler, now again, I'm not a PL person, but I do read your stuff. So this is written like a traditional compiler. It's even self-hosting. It's about 90 lines of RPL that parse RPL. In any case, we convert to a parse tree, convert to an AST, do macro expansion, simplification. There's an intermediate representation, and then we do code generation for a very, very simple matching machine, matching VM. In terms of performance, it's hard to know what to compare to, but here is another regular expression library-like thing. It's used in the Elasticsearch stack. Does anybody know Elasticsearch, Logstash, Kibana? Okay. So this is used all the time, and it was causing big slowdowns in the IBM cloud, and Rosie is about 4 to 5 times faster. Also, Grok, this other solution, I couldn't even run it on all my data because it failed with a UTF-8 error. This is real data. So all the data that was fed in here came from log files. And so, yes, your log files are going to have invalid UTF-8. What a surprise. Okay, one last thing. You all know what a Repple is, right? It's so nice to be in a room where people know what a Repple is. So the first thing I wanted to show was that if you replace the match command with trace, you can get a full stack trace, which you don't have to know how to read this, but if you use the system, you can use this to debug why a match failed, or even how it succeeded. Not so important as the REPL, where you can see what's in the environment, and you can match things and see the full match output, and you can define new patterns, and you can import and export stuff. If anyone's used a scheme REPL, it's got similar capabilities. These are the big things we've done so far. What we're working on now, I have a student who's implementing a theoretical algorithm for converting regex into parsing expression grammars. Actually, the theoretical algorithm is easy. What's hard is adapting it to real regex dialects so that we can take someone's collection of regular expressions written for Perl or Python or Ruby and actually use them here. I've got a prototype of ahead-of-time compilation. I had to write a cute little linker. There are optimizations there, though, that are whole program optimizations, and so if we want separate compilation, we have to think carefully about what we do there. We either put it all in the linker, which would be weird, or we do something else. Formal semantics would be nice. Given how many ways there are to go about that, I'm not sure which would be the most fruitful. And then finally, I've got a student working on static analysis. You'd be surprised at how rich this domain is for static analysis, but we can do things that we can't do with Turing-complete programming languages. You know, like we can look at an expression and give you worst-case runtime bounds. We can even generate examples that cause those. We can find common errors, and we can do other kinds of transformations. Okay, I got to finish up. I showed you examples that were all command line, but we have libraries in C and Python and Haskell and Go, and we used to, for an earlier version of Rosie, have libraries in these languages, and so we need to update them. If anyone has expertise and wants to volunteer, let me know. And that's all I had to say. Thank you.
So again, the mic is only for the cameras.
I saw the example you had shown for parsing JSON, I think it was. So I saw that, I mean, the syntax seemed pretty similar, at least the code part, to, compiler generators, like Lex, Yak, and Antler and all those.
Sure.
So I know they are for generating compilers, not for regular expressions, but could, in theory, those have been adapted using the same language to for Rosie instead of creating a new language as Rosie?
Yeah, that's a great question. We certainly could have adopted the syntax of Antler or one of the BNF processors or Yak or Bison, something like that. But it would have been difficult to actually use those parsers as implementations because there's a real fuzzy line between parsing and pattern matching. And I positioned Rosie as a pattern matching solution specifically because I didn't want users to have to understand much about parsing. I didn't want them to have to understand about operator precedence and separate lexical analysis and some of the other things that you would have to know about if you were using a compiler generator.
If I remember correctly, you have mentioned during your talk that it was a bad idea to use the strings to write your regexes, right? So how do we write a rows? How should I name it?
A Rosie pattern?
Yes, Rosie pattern.
Yeah, so if you have to use this pattern matching library from another programming language, ultimately you're going to pass a string to the librosie library. But the difference is if you have already written your pattern and named it in a file, you just pass the name. And so you can check that statically much more easily than you can check a pattern embedded in a string.
Hi, first of all, thank you for doing this. I think regex are one of the bad ideas that need to go sometime, right? But my question was about how did you select the expressive power of RPL? Like there are already existing 25 different variants, each with their own expressive powers. How did you go about figuring out what to put in your language and what not to?
Yeah, the question of what to leave in and what to leave out was difficult. What I ended up doing was kind of deferring that question by adopting the full definition of parsing expression grammars, which are essentially context-free grammars and more. But the way you express things in parsing expression grammars is sufficiently different than other CFG tools that it's more accessible, particularly since I borrowed a lot of regex notation syntax. It's more accessible to people who are not used to grammars and not used to parsing. But what I did do in terms of what to leave in, what to leave out, I made sure that you couldn't write anything recursive accidentally. So there's a separate construct called grammar and a block. And you can only have recursion within that block, which makes analysis easier because in many, many applications, you don't need recursive patterns, and you actually don't want them. And so we can do a lot of analysis on non-recursive RPL. And then when somebody uses recursion, right now there's a limited amount we can say about it, but that's going to change in time.
Thank you. Let's thank the speaker once again.
Thank you. Oh. By the way, I have stickers. I came from industry. We have stickers there.
So this is the end of the session. Now we have a break.
We're going to get